Assalamualaikum warahmatullahi wabarakatuh and good day to my fellow panel. Today I will be presenting about my project for PSM2 titled Extraction of Hydroxyapatite using Calcination method from waste fish bone for biomedical application. For introduction, my name is Muhammad Hilmi bin Zainudin. I am from program BMMA and my project is under the supervision of CS Azman bin Ibrahim and my co-supervisor Mr. Muhammad Saiful Firdaus bin Hussein. Without further ado, I will begin the presentation with the introduction to my project. Firstly, my project research is about implementing hydroxyapatite derived from waste fish bones towards the biomedical application industry. So what is biomedical? Biomedical is a working in the biological industry which relates to the medical treatment. In the scope study of biomedical, there are a lot of medical treatment involved which uses biomaterials such as metals, ceramic, glass, and polymers. The use of biomaterials such as polymers are very common nowadays, especially in the tissue engineering applications. This is because polymers contain wide range of physical properties and are adaptable to many applications such as drug delivery, medical devices, and bone tissue engineering. So what is tissue engineering? Tissue engineering is an application used in medical treatment for organ replacement, bone grafting, bone regeneration, and many more. The application only uses polymer that is crafted with proper structural, chemical, and mechanical needs towards the human body, which are called scaffold. This scaffold is then embedded in the human body as a substitute to provide cell growth and stimulate tissue regeneration. Now, to fabricate this scaffold, a biodegradable material is synthesized with the scaffold in order to not harm the human body when it is implemented. Natural polymers such as collagen, hydroxyapatite, and chitosan are biodegradable material that can be used to fabricate this scaffold. Hydroxyapatite particularly is a calcium phosphide mineral phase that naturally exists in bones. It is frequently used in a variety of medical applications due to its biocompatibility and bioactivity for bone regeneration. Moving on, I will now explain to you about the problem statement for my project. Firstly, medical treatments specialized in bone grafting today are in a very high demand. It is also very costly. The procedure is very complicated and the result is not very pleasing. This is because bone grafting is not the natural way of tissue regeneration as it takes other parts of the bone from the human body to replace at the broken bone. Other than that, there are limited sources of bone supply to the industry, and this has become a global crisis with the high demand of bone treatment around the world, especially people in the golden ages. Moreover, the extracted hydroxyapatite commonly used in the tissue engineering applications are mostly derived from mammalian bones. To exacerbate this problem even more, with the mad cow disease, nail and mouth disease, as well as religion boundary, has put a situation where we need a new source of hydroxyapatite that is capable to supply and meet the high demand of the people around the world. Now, I will explain to you about my project objective. The first objective is to analyze the potential of hydroxyapatite from fish bone for bone tissue regeneration using biometric study. Next, to prepare natural hydroxyapatite from byproducts through calcination process. And lastly, is to characterize the hydroxyapatite properties using FTIR, XRD, SEM, and EDS analysis. Now, for my methodology, this flowchart represents my guideline throughout my journey of finishing this project. The whole working process includes raw material selection, control parameters, material preparation, extraction process, and hydroxyapatite characterization analysis. Based on my bibliometric analysis results, I have chosen Sardina pilcardus as my raw material which I will be used to perform my project methodology. The Sardina pilcardus is purchased and obtained as byproduct waste from a fishing factory in Perak as there are abundant sources in this country. For the control parameters, based on my summary findings, different techniques of raw material preparation directly affect the bones and hydroxyapatite content. Therefore, the temperature and time of boiling phase and heat treatment must be controlled in order to produce potential hydroxyapatite properties. Furthermore, the trend of using calcination method to extract hydroxyapatite at temperature between 600 to 1000 degrees Celsius results in the formation of hydroxyapatite. Thus, temperature in this range will be the control parameters for this project during extraction phase. Now, I will explain to you the basic principle of extracting hydroxyapatite from waste fish bone that has been performed for this project. Firstly, raw material is obtained and cleaned with tap water. After that, waste fish bone will be removed from organic substances and fish flesh by boiling them for 1 hour in a large pot filled with water at 100 degrees Celsius. The bones are then cleaned with tap water again before setting them to dry at room temperature for 2 days to properly remove any remaining water and organic matter from the boiling process. Then the bones are stored safely in a polystyrene box. Next, we move on to the extraction phase. The bone sample is placed on a stainless steel tray and put into an oven set to 80 degrees Celsius for 5 hours. Then, identical bones were put into 2 crucibles and subjected to a calcination process. The calcination process was carried out in a furnace when the raw materials were heated to a temperature of 600 degrees Celsius for 5 hours at a rate of 5 degrees Celsius per minute. Once the calcination temperature is attained, the sample is naturally cooled in the furnace before transferred into another steel tray. And finally, the calcinated specimens are crushed using a mortar and pestle until exhibit powder form. The hydroxyapatite powder is then securely stored in a plastic container for later investigation and characterization. Next, we'll move on to the characterization phase. A couple of machines is used to characterize the obtained hydroxyapatite powder. These include Fourier transform infrared spectroscopy, FTIR, which is used to characterize natural hydroxyapatite functional group. Apart from that, X-ray diffraction, XRD analysis, will reveal the mineralogy of the powder and verify its purity and stability phase. Next, powder sample is to be coated with platinum using a coating machine which acts as conductivity during scanning electron microscope SEM analysis. SEM will then evaluate the powder's morphology and microstructure. Lastly, using identical coated samples, energy dispersive X-ray spectroscopy (EDS) will identify the powder's chemical composition and compute its stoichiometric ratio. This analysis result is then connected and discussed to characterize its potential use in biomedical applications. So that is the basic principle of my project methodology. Now we can move on to the result and discussion section. This study seeks to perform bibliometric analysis to review an alternative source of hydroxyapatite and establish an effective methodology of extracting them with the help of prior published literature between 2010 and 2020. As you can see, keyword research is performed and the result is tabulated in this slide. Keyword analysis revealed that the term biomedical had the greatest cumulative publication of all the chosen keywords. The number of articles containing the term biomedical rose by 74% during a 10-year period. Other than that, a total of 24 publications related to this study under the keyword combination of hydroxyapatite plus fishbone plus biomedical have been identified through Scopus database. Next, we can review the trend of publication based on the keyword research across the 10-year period. This graph illustrates the trend in the number of publications based on keyword research in the Scopus database. Each year, the pattern rises in the number of publications. This proves that hydroxyapatite is a relevant topic to explore in terms of fishbone, calcium phosphide, and biomedical area of study. The data analysis seems to demonstrate a linear increase, indicating a continual growth rate of publications in this study field. Next, we can review the country research analysis based on the highest level of publishing research papers related to hydroxyapatite in biomedical. As the bar graph shows, China dominated, publishing 515 papers on hydroxyapatite research in biomedical. India and the United States are the next most active nations with 440 and 247 publications respectively, while Iran and Malaysia include the top 5 countries generating the most hydroxyapatite biomedical scientific articles with 146 and 143 publications respectively. As seen in this slide, collaboration across countries on hydroxyapatite biomedical articles was built using viewer software. The cluster analysis demonstrates highest collaboration between China and India, while collaboration between the United States, Malaysia, and the United Kingdom ranked second in terms of publishing scientific papers related to this area of study. The collaboration connection between other European and Middle Eastern nations seems to be limited, meaning that there are not many hydroxyapatite biomedical papers published in this region. Last but not least, keyword co-occurrence analysis is performed based on articles related to fishbone hydroxyapatite in biomedical area and calcium phosphide in biomedical applications. The analysis conducted utilizing cluster patterns through post-viewer software. The left cluster analysis represents the keyword of fishbone hydroxyapatite in biomedical paper, while the right represents the keyword of calcium phosphide in biomedical application papers. Both cluster analysis exhibit biomedical cluster dominance. Now, we can move on to the second part of the result and discussion. For hydrostatic characterization analysis, there are 4 properties that have been chosen and analyzed for this project research. The 4 characteristic properties are functional groups, crystalline phase, morphology characteristics, and chemical composition. This analysis is carried out using FTIR, XRD, SEM, and EDS equipment. In general, FTIR technique is used to characterize the functional groups contained in powder samples. This analysis reveals the phase composition of hydroxyapatite powders generated through calcination at 600 degrees Celsius for 5 hours. From the graph obtained, we can observe the typical FTIR spectra of the sample bands corresponding to hydroxide, phosphate, and carbonate. This study indicates that the organic component of the raw bones was eliminated, and the powder sample produced a pure hydroxyapatite, which indicated by the presence of distinctive peaks. Moreover, natural hydroxyapatite derived from sardine bone in this research may have high biocompatibility and appropriate morphology for use in biomedical applications. Next, powder samples, purity, stability, and crystalline phase is examined through XRD analysis. Hydroxyapatite, beta-tricalcium phosphide, and calcium oxide are the control parameters elements for this analysis. The graph in this slide depicts the atomic structure of powder samples calcinated at 600 degrees Celsius. The graph demonstrates wavy pattern which suggests a significant concentration of crystalline hydroxyapatite mineral. This is because calcination process enhances the crystalline structure of hydroxyapatite powders, resulting in a peak pattern. It is also believed that hydroxyapatite was derived during calcination process due to the crystalline particles tendency at elevated temperature. Moving on, the study of hydroxyapatite morphology is performed by SEM analysis. SEM produces a magnetic picture by scanning the powder sample with an electron beam. Before mounting the sample on a stage to the chamber area, it is coated with platinum using a coating machine, which acts as a conductivity during analysis. The image of the powder sample is presented here. Visual examination result reveals that the hydroxyapatite powder exhibits a spherical morphology with an average particle size of 300 nanometers, which is crucial for tissue engineering applications. Last but not least is the EDS analysis, which will determine the chemical composition of hydroxyapatite powder samples. This approach also entails coating the powder samples with platinum to increase their conductivity, then attaching samples to a conductive platform before mounting them on the stage in the chamber area to determine their element composition. Based on the finding for EDS analysis, the CAP ratio is calculated using the displayed formula. Table of results is also displayed, which summarizes the finding on powder samples chemical composition. EDS results show that CAP ratio obtained was 0.697, which is less than the stoichiometric ratio necessary for pure hydroxyapatite. This could be the side effect of surrounding elements and phases during analysis. Based on the results, it can be concluded that hydroxyapatite extracted from waste fish bone for sardine exhibits a great potential use in biomedical applications, particularly in tissue engineering. This is because calcination process is an intelligent approach of extracting hydroxyapatite due to low cost, simple, and has a satisfactory degree of biocompatibility. Based on this research finding, it can be concluded that deriving hydroxyapatite at 600 degrees Celsius from waste fish bone resulted in the production of carbonated natural hydroxyapatite, which is desirable for a variety of biomedical applications. Apart from that, functional group proved that the powder is biocompatible and has the appropriate morphology. However, the stoichiometric ratio determined by EDS analysis was less than the theoretical hydroxyapatite stoichiometric ratio, and the powder sample is described as white with a slight black shade. And here are the following list of future work improvement, accuracy, and thoroughness improvisation that could be taken to enhance the research related to hydroxyapatite extracted from waste fish bone for biomedical applications. That is all from me. Thank you for watching.